Okay, thanks everybody. Our next speaker, it's my great pleasure to have Jan Dierzynski from the University of Warsaw giving a talk today. So he's going to talk about one-dimensional Schrödinger operators solvable in terms of the confluent and hypergeometric functions, something of great interest to me at least. So I hope you enjoy it as well. So Jan, take it away.
So thank you. Uh, so um, uh, let me first say what I mean by Schrödinger operator. So one-dimensional Schrödinger operator, which I, for brevity, call a Hamiltonian. This will be an operator of the form minus the second derivative plus the potential. Now, the potential can be complex. I mean, usually in quantum mechanics, one considers real potentials, but I mean, it is actually interesting to see that the theory with complex potentials is almost the same. Um, Now, I will be interested in closed Schrödinger operators acting on a Hilbert space of L squared of an interval. The interval can be infinite. And so closed having a non-empty resolvent set. Now, so resolvent set is the complement of the spectrum. So for a complex number in the resolvent set, you can define the resolvent, and its integral kernel will be called the green function. And I will describe 14 families of Hamiltonians with green functions expressible in hypergeometric class functions. These families are on a formal level well known in the physics literature. In fact, if you look at a collection of problems in quantum mechanics, you will find most of them or even all of them. And if you study quantum mechanics and you have you must have seen at least a few of them. And if you had an ambitious teaching assistant, you may have seen even more of them. Um, but most of the literature is kind of formal without functional analysis. And in my presentation, I mean the functional analysis aspect will be important. My talk will consist of two parts. In the first part, I will speak about Hamiltonians reducible to the Whittaker equation or to Bessel equation, which is a special case of Whittaker equation. And this is joint work with Jinhyop Lee. The second part will be about Hamiltonians reducible to hypergeometric equation. And this is joint work with Pedram Karimi. I mean, there will be, as I said, 14 families. Here here is the list of them. So, I mean, this talk is for lovers of botany or ornithology. So for people who like to watch various species of plants, birds, and operators. So the first two types are so I listed them. Um, there are two types reducible to the Bessel equation, then three to Whittaker equation, which is kind of a larger class, and then okay, let me continue. Now, a typical situation will be like this. So there are some parameters in the problem, and one can ask whether a given formal expression corresponds to a unique closed realization. so whether you, whether you have to set boundary conditions or not. Now, it turns out that in many cases, you don't have to fix boundary conditions, and you have a kind of a unique closed realization of an operator, and then you can analytically continue this family to a region where you don't have the uniqueness. Now, okay, let us start with the first part of my talk. So these are one-dimensional Schrödinger operators solvable in terms of Bessel and Whittaker functions. So this is in collaboration with Geniop Lee. So I'm not sure whether the Bessel equation is belongs now to the curriculum of mathematics faculties, but so here it is. Well, I think in physics faculties it is still taught. Actually, this is the modified Bessel equation, which so the usual Bessel equation has a different sign at one place, but the standard solution is the so-called modified Bessel function, which is denoted I sub m, and m is an arbitrary complex number. And there is another solution, standard solution, which is, well, I mean, they have many names, but the name that I will use is the McDonald function, and the symbol is k sub m. So the modified Bessel function is characterized by its behavior near zero. So here it is roughly the power of r, and the McDonald function has a good behavior at infinity. So roughly speaking, it decays exponentially. Now there is a different equation which is very closely related to the Bessel equation. It is sometimes called the one-dimensional Bessel equation. So here it is on the slide. And it is also solved by the Bessel function, I mean, by the McDonald function, but you have to multiply by the square root of r. So here, and I will denote them by the calligraphic letters. So this will be used shortly. So here is the first family of Schrödinger operators that I will consider. So the name which is common in the literature is the Bessel operator. So it is the operator with the potential 1 over r squared. So you have to, so one can see that this is a homogeneous expression, homogeneous of degree -2, and it is important that the coefficient in front of the potential is written as m squared minus 1 over 4. Now, this is, so the, and m, as usual, in my talk, everything will be complex. So m is a complex number. So the thing which one can show is that if the real part of m is greater than or equal to 1, then this expression, this formal expression, has a unique closed realization on L squared of the positive half line. Well, for instance, here there is a mistake. If m is greater than 1, there is a misprint. H sub m is essentially self-adjoint on compactly supported smooth functions. But more interestingly, it extends to a holomorphic family for m greater than, for real part of m greater than -1. You can compute its green function. So here there is a formula. So as you see, I hope this is self-explanatory. You have the resolvent of the Bessel operator. The spectral parameter is minus k squared. X and y are two variables in the positive half-line, and you have the expression in terms of one-dimensional Bessel and McDonald functions. This was the first species of operators. The next species. Consider the exponential potential. The kinetic energy plus the exponential times a coupling constant, which is written as k squared. Now, here, if we assume that the real part of k is positive, then again, there exists a unique closed realization of this formal operator. You can compute its green functions. So you have this expression in terms of the Bessel function and the McDonald function. Now, you may wonder why on the previous transparency, the parameter was called M and the spectral parameter was called k squared. Now it is the other way around, but there is a reason. So there is a curious relation, I call it a transmutation relation, which links green functions of the two above families of operators. So the green functions of the Hamiltonian with the exponential potential is related to the green functions of the Bessel operator by the formula on this slide. So this is not how to say, not a similarity relation. These operators are very different, but there is a relation between them, and in this relation, the coupling constant becomes the spectral parameter and the other way around. So, well, maybe it's funny, but let's continue. Now, Whittaker equation. So I'm sorry, I have to give a crash course on the Whittaker equation. So this is it is written on the slide. It is essentially the eigenvalue equation for the Coulomb problem, for the radial Coulomb problem, and it is closely related to the confluent equation. Now, the confluent, there exists two kinds of the confluent equation. The usual one, which is sometimes called Kummer's confluent equation, has a solution which is f11 function, but there is another another type, and I will explain this on the next slide. So here you see the confluent equation. It has a standard solution which is called the confluent function. So here it is. There is also an equation which also can be called confluent. It is rarely seen in the literature. Now, so the confluent equation has a regular singular point at 0. Now, this other equation has a regular singular point at infinity, and at 0 has an irregular singular point. And it has a standard solution, which is called f20 function, which is not analytic at 0. It has a branch point, and it has an, I mean, it has an interesting asymptotic expansion near zero. Now, we will need two pairs of, okay. Now the Whittaker equation, I mean the Whittaker equation was here. So it has two standard solutions which can be expressed in these two kinds of confluent functions. So my notation for these functions should resemble the notation for the Bessel function. So I is kind of an analog of the modified Bessel function, and K is an analog of the McDonald functions. Again, I is characterized by the behavior near zero and K near infinity. And there will be some cousins of these two functions, which are given here. So you multiply by something trivial, or you change the variable in a trivial way. I mean, we will need three pairs of functions. Okay, so now a new species of exactly solvable Hamiltonians. So this is sometimes called the Whittaker operator. So it is very similar to the Bessel operator, which we discussed a while ago, but in addition, it has the Coulomb potential. So this is the operator which you obtain from the in the hydrogen atom when you solve the hydrogen atom. And so this is the radial part of its Hamiltonian. The theory of this Hamiltonian is very similar to the Bessel Hamiltonian. So again, for m greater than 1, there exists a unique closed realization, and it extends to a holomorphic family for the real part of m greater than -1. Now, there is actually a funny new phenomenon, which is a singularity at 0 minus 1/2. So at beta equals 0 and m equal -1/2. And I will explain this singularity. And there is a formula for the green functions, which uses both kinds of Whittaker functions. Now, let me say a few words about the theory of this equation. So there is an identity. So if you change if you take 1/2, so m is 1/2. So you should note that if m is 1/2, then this centrifugal potential, so 1 over r squared, vanishes. So it is a special point. But suppose that the centrifugal part vanishes, but the Coulomb potential does not vanish. Then it turns out that you have the identity that m equal 1/2 and -1/2 are the same. This is an identity which is not true for beta equal 0. So if you don't have the Coulomb potential, then you don't have this. And actually, for beta equals 0, the Bessel operator is a special case of the Whittaker operator. So, and the -1/2 case is the Laplacian on the half-line with the Neumann boundary condition at 0, and for h1/2, it is the Laplacian on the half-line with the Dirichlet boundary condition at 0. As I said, 1/2 or -1/2 means that there is no centrifugal term. Now, it is clear that the Neumann that the Hamiltonian with the Neumann condition and Dirichlet condition are different. So this means that for beta equals 0, the identity on the top of the slide is not true. And this implies that the Whittaker operator has a true singularity at this funny point. Next, the Schrödinger operator with the Morse potential. So again, so you have two exponentials, so e to 2x and e to x. So this is one of favorite potentials for ambitious teaching assistants on quantum mechanics. So again, for real part of k greater than 0, it possesses a unique close realization on the whole real line, so in L squared of R. And you can compute the green function that's using another kind of Whittaker functions. Finally, the isotonic harmonic oscillator. So here, so I mean the harmonic oscillator is the square v. So here the variable is called v. So v squared. Now, so suppose you have a two-dimensional harmonic oscillator with the same frequencies in both x and y variables. Then you can separate the variables in the polar coordinates, and what you get is precisely this this operator. So isotonic means that the tone, the pitch, is the same in the x direction and in the y direction. That's this is one of many names of this exactly solvable Hamiltonian. And again, the theory is very similar to the Bessel operator for the real part of m greater than 1. It has a unique close realization, which extends holomorphically to the real part of m greater than -1. And we can compute its green functions, again, using another variety of Whittaker functions. And we have transmutation relations. So we have three green functions, and you can pass from one green functions to the other, and essentially by permuting the three parameters. So you have the parameters are k, m, and beta, and you choose two of them as the parameters of the Hamiltonian, and the third parameter as the spectral parameter, and then you have then you write the green functions, and you can pass from one to the other. So that's maybe this is entertaining. So this is this is all what I wanted to say about Hamiltonians reducible to Whittaker or confluent equation. I mean, Whittaker and equation is equivalent to the confluent equation. So that's so. Are there any questions so far? So next, the second part will be devoted to Schrödinger operators solvable in terms of hypergeometric functions. So it is joint work with Pedram Karimi. Now, the hypergeometric equation, I mean, is the equation. I mean, instead of the full equation, I'm writing the operator which defines this equation. As you see, this depends on three parameters, A, B, and C. We also have the Gegenbauer equation, which depends on two parameters, alpha and lambda. Now, the Gegenbauer equation is essentially a special case of the hypergeometric equation where you put so in the hypergeometric equation the singular points are at 0 and 1, so which you see because of this prefactor z times 1 minus z in front of the second derivative. Now, in the Gegenbauer equation, you move these singular points to minus 1, 1, and besides in the case of the Gegenbauer equation, you have a symmetry. So this is an equation which is invariant with respect to the change w, so goes to minus w. So that's and of course, solutions of the Gegenbauer equation can be expressed in terms of the hypergeometric function. So I will describe 9 families of one-dimensional Schrödinger operators, which are reducible to the Gegenbauer or hypergeometric equation. Now, here I listed them using the names which we introduced. So these are not the traditional names. So there will be the Gegenbauer Hamiltonians, hypergeometric Hamiltonians of the first kind and of the second kind. And each will have 3 types, which we call spherical, hyperbolic, de Siterian. So that's, I mean, I will try to justify these names. I mean, at least this is quite a symmetric list of names, and that let me. These Hamiltonians have traditional names, which are so they are named in most of the physics literature. They are named after some physicists who discovered these Hamiltonians. So, for instance, the Peschel-Teller is one of some of these Hamiltonians are called after Peschel-Teller. So it is, but in fact, in the literature, each Hamiltonian may have different names depending on the source. Okay, so let's start with the Gegenbauer Hamiltonians. So how to produce a Schrödinger operator from a second-order differential equation, or one can say from a Sturm-Liouville operator. So in fact, both the Gegenbauer operator and the hypergeometric operator are examples of what's called a Sturm-Liouville operator. So you can put some weights on both sides of the Gegenbauer operator. And I mean, if you do it in a clever way, you can write it as the square of the derivative multiplied by a weight plus a potential. A potential means a function. Now, then you can make a change of coordinates, which transforms this derivative term as into as the second derivative with respect to a new variable. And then you restrict this variable to an interval, and you get a Schrödinger operator. This is in the mathematics literature called the Liouville transformation. Apparently it is due to Liouville from the 19th century. Now, here I described the Liouville transformation for the Gegenbauer operator, and then the variable w is can be complex. But to get a Schrödinger operator, you want a real variable, so you choose and you can choose this variable in several ways. So here there are three proposals with the names. So the spherical case corresponds to the to choosing this variable w in a finite interval, the hyperbolic in a half line, and what we call Desiderian in a on the imaginary axis. After the application of this Liouville transformation, you get three kinds of Schrödinger operators. Which we call spherical Gegenbauer. So it has the potential 1 over sine squared, and it acts. I mean, to get a good theory to compute the green functions, one can consider a squared of the interval 0 to pi. Then there is hyperbolic Gegenbauer Hamiltonian when you have sinh squared, and what we call Desiderian Hamiltonian with 1 over cosh squared. I mean, in this talk, I will not describe the green functions. I mean, this is probably, I mean, in my talk, there are so many formulas that I will not give green functions now. But let me mention that these three types of Hamiltonians have a very nice geometric interpretations, which you probably know. So the Laplacian on the sphere on any in any dimension in spherical coordinates becomes the spherical Gegenbauer Hamiltonian. So you take the Laplace Beltrami on the sphere, you separate the variables, you restrict to spherical harmonics in a part of the variables, and in the main variable you get the spherical Gegenbauer Hamiltonian, where this number alpha depends on the dimension and the angular momentum of the spherical harmonics. If you do the same with the hyperbolic space, again, hyperbolic space of any dimension in spherical coordinates, then you get the hyperbolic Gegenbauer Hamiltonian. So instead of sine, you get a sinh. If you do a similar thing, so the de Sitter space, I'm not sure if the de Sitter space is a famous Lorentzian manifold. So it is so physicists believe that our universe can be modeled by the de Sitter space, and in particular, I mean, our universe is expanding, and this is well captured by properties of the de Sitter space. So this is a Lorentzian manifold, Um, mathematically, it is the one-sheeted hyperboloid. It has a natural D'Alembertian, and you can separate the variables in this for this D'Alembertian, and you obtain this Schrödinger operator, and that's why we call it the Siterian. Now, this is a well-known Schrödinger operator for many reasons. So if alpha is if alpha is a half integer, then this is an example of a Hamiltonian which is reflectionless, so which is a very curious property. So that's so it's there is a lot of literature about this. Okay, let's continue with the now the Gegenbauer operator had two parameters, and the one parameter was used in the potential, so alpha enters the potential, and the other parameter was used as the spectral parameter, so it was lambda squared. Now, the hypergeometric equation has three parameters, and instead of A, B, C, I will use alpha, beta, mu, which in some sense are more natural. So here, again, I'm putting some weights in front and after the hypergeometric operator, and then I obtain something in the Liouville form. So there is the square of the derivative times a weight plus a potential. Actually, the potential depends on two parameters, and then there is the something which can be interpreted as the spectral parameters, which is so mu squared over 4. So then, as before, I restrict this to an interval, and there will be three choices: a finite interval, a half line, and a line. So in this case, this will be a line, a vertical line passing between 0 and 1. I mean, and the names, we keep the same names as before: spherical, hyperbolic, de Siterian. Maybe this is not the best choice, but if you suggest me a better one, I will maybe use it. So now you have three kinds of hypergeometric Hamiltonians of the first kind: the spherical, hyperbolic, and the Siterian. Spherical has sine and cosine. The hyperbolic has sinh and cosh. And the de Siterian is, well, there is also, maybe it looks more complicated, but it's actually also the same spirit. So all of them depend on two parameters, and you can compute the green functions which are in our paper, and all of them have a natural geometric interpretation. Now, if you take the Laplacian or the Laplace-Beltrami operator on the sphere of any dimension, so this dimension I wrote as P plus Q, then you can suppose you split the variables into two groups. There are there is a coordinate system which can be called a double spherical coordinate system. Actually, there is a misprint. It should be S to P plus Q minus 1. So the ambient space has to be P plus Q dimensional. You take P variables in one group, Q variables in this second group. Then there is a relative a variable which kind of essentially is the ratio of two radii, and you separate the variables and you get the spherical. Oh, I'm sorry. I'm very sorry. Yeah, so if you do this, you get the spherical hypergeometric Hamiltonian of the first kind. If you do the same on the hyperboloid, where you have two groups of variables, and the first have a negative signature, the second group has a positive signature, then you get the hypergeometric hyperbolic Hamiltonian of the first kind. Now, the most funny construction is for what we call the Siterian hypergeometric Hamiltonian. And unfortunately, I don't have a slide on this, but I recommend you to look at the paper, because this is, I have never seen a similar construction, but well, that's not very difficult. You just consider complex coordinates, and then you have something like the complex sphere, and the two you have holomorphic coordinates, holomorphic Laplacian and anti-holomorphic Laplacian on this complex sphere, and this leads to this funny Hamiltonian, which actually it was not completely obvious to obtain that. Next, there is a hypergeometric family of hypergeometric Hamiltonians of the second kind. Now you do, I mean, you do a similar thing as for the first kind, but you can see that there are different weights which are used to multiply the hypergeometric operator, and there is a different. You get a completely different expression, which is also in the Liouville form. Then you choose an interval, a finite or semi-finite, or a line with these variables, and you get three families of hypergeometric Hamiltonians, which again we call spherical, hyperbolic, and Siterian. They look like the Gegenbauer Hamiltonians. I mean, if you remember, they look, but they have an additional potential. So you see that here there is a well, what is it? It is a cotangent. Here you have again a cotangent hyperbolic, and here you have tangent hyperbolic. So these are additional potentials added to the to Gegenbauer Hamiltonians. Now, I mean, let me pose an open question, which I don't know how to, well, maybe I know, at the moment I don't know how to solve it. Find a geometric interpretation of hypergeometric Hamiltonians of the second kind. So as I mentioned, for the first kind, we have a very nice geometric interpretation. Now, what I mean by a geometric interpretation, I mean that these Hamiltonians should be derived by a separation of variables from an invariant differential operator on some symmetric space. So, for instance, the Laplace-Beltrami operator on the sphere, it gave the spherical hypergeometric Hamiltonian of the first kind. Now, my conjecture is that here you cannot use a second order differential operator. You have to use a fourth order differential operator, but I haven't worked out this, so that's still an open question, and I invite you to think about this. No, and again, we calculated green functions, and which I will not give. You have various identities. You have coincidences, which are here listed. So if you take the same parameters for in the Hamiltonians of the first kind, you get the Gegenbauer Hamiltonian. If you put 0 in the here in the second kind, you get again Gegenbauer Hamiltonian. So there are relations. There are also curious relations which are similar to the one that I mentioned for the Whittaker Hamiltonian. So that here they are. So again, you have some strange singularities of these holomorphic functions. So let me, maybe I didn't explain this, but so what all these families are holomorphic, which essentially means that the resolvents of these holomorphic families are depend holomorphically on the parameters. There are also many transmutation relations. I mean, here it is really a zoo of transmutation relations. I don't have slides about them. I mean, that would be probably overwhelming because there are so many. And it is related to the fact that the hypergeometric equation is very symmetric, so you have many symmetries. And I think this is the last slide, so thank you for your attention.
All right. Well, please join me in thanking Jan for a great talk. All right, so let me stop the recording real quick.